Thank you, Jason. Thank you, and thanks for coming tonight. Amazing venue here at Autodesk. It's a great place to be. Well, we're going to start off a little bit serious. Why? Why are we starting off on this serious note? And it's a really important question because it really gets to the heart of who we are at ArcSpax, where we came from. As Jason mentioned, I'm an architect and a builder, and we've been looking for a better way to build, for quite some time. ArcSpax comes from the Latin. The words mean citadel and peace, and that gets to the heart of what we do at ArcSpax. We look at it as our responsibility to build more responsibly, particularly in areas subject to earthquakes, floods, tsunamis, Mother Nature's bad days. And these ideas were born just a few miles south of here in the Mission Bay, inspired by the houseboats in China Basin. How does this relate to magnetic field architecture? Well, I'm going to get to that in a moment, but first we'll lighten it up a little bit. So who are we? As Jason mentioned, we are the inventors of magnetic field architecture. This is the more efficient combining of magnetic fields, and it can result in being able to apply a force across a distance. What does that mean? Being able to apply a force without touching something, to more efficiently transmit electromagnetic energy, right? And it's going to take a while for this to sink in, but the results are amazing, and it enables things that have been previously impossible, like Tony's ride here on a hoverboard. But that's just the beginning. I said this was inspired by a project in the Mission Bay. It was a design project at Cal in grad school. We were designing a school in the Mission Bay. Okay, if you know anything about, and I know there's a bunch of designers and architects in the audience, not the best place seismically to build a school. But what if you can separate that, decouple that structure from the earth? If we look at the state of the art for seismic design, it's something called base isolation. Base isolation, using huge friction pendulums and rubber isolators, is a way of transforming kinetic energy from the short, fast shaking of an earthquake into a long, slow shake that a building can tolerate. That's the state of the art, right? And it works very well, and it's been a great step. But there's a better way. Probably the most cost-effective way is this. We build a containment vessel, a shallow pool. We add water, which becomes a buffer medium, right? We're floating a 3-story building in 3 feet of water. It's a very simple idea, but we received a patent for it last year. We did not apply for this patent overseas because there are places now that need this technology. This is available right now. Places like Micronesia, islands disappearing. This is really important stuff. But in taking a better look at that buffer medium, we asked, if you can hover a 50,000 kilogram train, why not a house? As a way of separating something from the earth. And it turns out there was no good way. If you can imagine a train, you have a train, but you want to levitate a stationary object. And that's the big challenge. There was no good way to levitate a stationary object, a stationary object with a dynamic payload. But you have a train. So what do? Imagine for a moment if that train went in a circle. Now imagine that train was the same length as the track. You take that concept and you shrink it down. That system is stationary relative to the earth. And that's what we're talking about. And that's what went into our hover engines. How does it work? Well, in this white box, I'm going to demonstrate in just a moment, but we take a hover engine. That hover engine generates a primary magnetic field, okay? When it's moved relative to this conductive plate, and it can be copper or aluminum, a non-ferromagnetic material, it creates swirls of electricity. Swirls of electricity in a closed loop, very high amperage. And those swirls of electricity, called eddy currents, in turn generate a secondary repulsive magnetic field. And that's what generates lift. And it can do a lot of other things as well. We can take some of that lift, and we can redirect it and capture some of that force and direct it for propulsion and control. Now, here's where it gets really interesting. The idea of connectivity, right? It changes everything. We are changing the fundamental rules. We've had the wheel. The wheel has served us really well. Well, this has a whole other host of opportunities. It's really just the more efficient transmission of electromagnetic energy. And that enables things in all sorts of other areas that wouldn't naturally come to mind. So, whether we're talking about how we live, how we move from place to place, and how we move things, how we learn, how we make things, how we play. You've heard the term wearables? Well, Orcspax is about to introduce the concept of movables. And trust me, it's going to get very, very interesting. So you saw Tony riding the hoverboard. If you can imagine for a second your smartphone. Your smartphone, it knows you. My smartphone knows me probably better than my mom does. It knows how you like to move. What kind if you could take a smartphone and program your favorite mode of transportation, your bicycle, your skateboard, however you get around, this thing can translate into how you like to move, how fast you like to go, how tight you like to cut corners. That's all possible now. There's some amazing, amazing applications in virtual reality. One of the things we did early on was we take the hoverboard and we put a chair on it. And you close your eyes and you swear you're flying. If you ever wanted to know what it's like to be disconnected from the earth without hearing the sound of rushing air or blowing wind, it is really something. And when you combine that with a virtual reality headset, it's a potential to disrupt the entire amusement park world. If you can just go down to your local arcade versus going to Disneyland, it's going to shake things up. Industrial automation. Since we launched our Kickstarter campaign last October 21st, which is sort of a magical day, it's coming up again, October 25th or 21st, the day that Marty McFly shows up in the future in the series Back to the Future. No accident. Well, the biggest amount of inbound interest comes from this, from industrial automation. This is the scientists calling from the research shops at all the big companies you've ever heard of. You think about Henry Ford and his assembly line. His assembly line that created the Model T in 1913, 100 years ago. 100 years we've been working with the assembly line, this linear process that is, by its very nature, limited. One single point of failure along that line, and the system comes to a halt. What if? What if there's a new way to build? A manufacturing network, an assembly network, where the operator, the equipment they need, the part, and the object they're working on all arrive at the appropriate time and place and move together to make the whole system more efficient. That's the kind of thing we're talking about, and that's why these folks are reaching out. They know that because we can now move in any direction, we have our own inherent system of propulsion and control. We're about to redefine how things are made, and it's going to be amazing. Okay, this gets most near and dear to my heart. This is a video that's showing the Napa earthquake as it occurred last year. All right? That expanding yellow line is the primary wave, the compressive wave that travels faster than that red secondary wave, which is the destructive secondary wave. Now, you saw we had over 20 seconds of time, of warning, to our lab there in Los Gatos, California, about 50 miles south of here. Well, that's the Napa earthquake. If it was the San Andreas, which is just 5 miles south of our location, we would have had about 2 seconds. But 2 seconds is all we need. 2 seconds for the early warning system, Shake Alert by UC Berkeley, in beta status right now, to activate our hover systems. All right? Hover systems are located under a piece of precious art, an expensive piece of equipment, a lithography machine, an operating table, anything precious that needs to be protected. An entire building, a room within a building. The alerts received, the hover engines activate, the landing gear retracts, the ground starts shaking, the ground finally stops shaking, the landing gear returns, and that object experienced no movement whatsoever. The possibility of perfect seismic isolation. And again, that's our goal. That's what we're looking for at ArcsPax. And we have 2 seismographs in our conference room, and we are exploring this potential right now. Transportation. Who's heard of the Hyperloop? Wait till you see our solution. The Hyperloop is a great idea. We are big fans. In fact, I want to hand it to Autodesk. Autodesk Fusion 360. There's a bunch of interns who've been working really hard on this concept. And Fusion 360 is a great tool. And I think it's going to help accelerate things. If you have a vehicle, a pod like this, that's enabled with magnetic field architecture, all right, you board, let's say, this pod outside of Los Angeles. 20 minutes later, you're outside of Vegas. But instead of like an airplane, you get off the plane, then you go get in the cab line, which could be an hour long. You stay in the pod. You arrive outside of Vegas, you leave the tube, you hover down the strip and right into the casino, solving the biggest bugaboo for mass transportation, the last mile challenge. Sharing infrastructure with other vehicles that are enabled. We have a hybrid vehicle that can drive conventionally or hover, because there's no more efficient way of getting from point A to point B right now than a train. But how do you get from point B to your final destination? That's what we're talking about, solving that last mile challenge. Our vehicles can move in any direction. They can share infrastructure. The Hyperloop, as it's designed, gives you about 500 microns. Okay, I'm not a scientist. I had to look it up. Okay, that's half a millimeter. Half a millimeter of hover height at 700 miles an hour. We'll give you 25 millimeters for less cost. So, connecting the future with magnetic field architecture. Now, if you haven't seen our demonstration out in the gallery, I invite you to come up afterwards and touch it. Because when you touch this technology, when you feel the resistance, it will change your perspectives. Because we are just now changing the rules. So, to give you a little demonstration right now, this is our white box. It's my favorite prototype. This is a couple years old now. It's got many, many flight hours, if that's what you call it. But this is the generic embodiment of our technology. Okay, there's 4 hover engines in here, and as you can see, it's solid. I'm going to turn it on here. Oh, yes, absolutely. How's that? Good? Okay. So as I was saying, my favorite prototype, and this thing's been around the block a couple times. So, a little noisy. By the way, we're working on a solid state version, which would be, of course, very silent. No friction. No friction. Have you ever seen anything bounce in midair? So you can start wondering, what could you do with this technology? And what's really exciting is this is what we're going to be delivering here very shortly to our Kickstarter backers, a developer kit. It is designed to take apart, to explore, because we know that there are problems out there that we don't know anything about. That's why we want to put it in your hands. Your hands. We want to inspire global development of ideas. Collaboration across borders. Let's figure out what these problems are that we can solve and get to it. Now, I'd like to ask, I think that it's not typical, but we'd love to entertain your questions. Does anyone have any questions? Yes, sir.
Ground plane infrastructure, what do you need?
Ah.
On? Yeah, so the ground plane infrastructure, what do you need?
Great question. The question is about the infrastructure, all right? So right now you can look out the window here and you can see the trillions of dollars invested in the infrastructure that the automobile requires, right? What do we need? We need a conductive surface. A conductive surface. This is vinyl-covered copper. Now, it's based on conductivity. That's what allows the eddy current formation. And so relative to copper, we need something very conductive. On the conductivity scale, there's silver way up here at the top, 106% IACS, percent of the conductivity of copper. Copper's about 100, gold's about 70. Aluminum ranges, depending on the alloy, 40 to 60. Plenty to generate what we would like to generate. So using aluminum. But you tap into something there, sir, that's really exciting for me. Let me give you an idea, and it's not my idea, but I love it. Actually came from David Brin, the sci-fi author. What if we could sequester the carbon in the atmosphere into substances like graphene? Graphene, right? If copper's here and silver's here, graphene's way up there. What a perfect solution for a situation with carbon in our atmosphere. Any other questions? Yes?
So you said that you did not apply for a patent for your technology in other countries, but has it been implemented in any of those other countries?
No, and I want to be really careful and specific. Thank you for the question. We have not applied for international rights to the three-part foundation system. This is a low-tech solution that we invite people to use in the third world, for instance. They can use it now, that's fine. If you want to build it here in the Bay Area, for instance, let us help. However, we have applied internationally for, in fact, we've just recently been granted several patents for magnetic field architecture as our core technology, and that has been filed internationally. Yes? Great questions, by the way. And this is, for me, this is the part that I really appreciate. It's no fun talking about the other stuff. I want to answer the questions.
So on the earthquake solution, it would seem that presumably the amount of power needed is going to have something to do with the size of what you're protecting.
Oh, I love that question.
But obviously, in an earthquake, a power cut is one of the concerns, right? So how does all that work?
Thank you. That's a great question. So first of all, there's a lot of ways to store power. For an earthquake, you don't want to rely on the grid. Okay, so how much power do you need for 50,000 kilograms? Well, we've done the math. For 90 seconds, or the duration of an average shaker, 90 seconds, we need about 50 kilowatt hours. PG&E peak rates, $13.10 for 50,000 kilograms for 90 seconds. How do we store it? How do we store it? We can use batteries, okay? That's, by the way, 50 kilowatt hours is the energy stored in 5 car batteries. We need to get it out a lot faster than a car battery can provide, and there's some great systems to do that. There's thermite batteries. But there's also a whole bunch of other ways to store energy. The hover engines in this box operate at an efficiency of about 40 watts per kilogram. If you want to push air, a helicopter is about 160 watts per kilogram. How do they store energy? Chemically. We'd rather not burn fossil fuels to power our hover engines, but we could. Sir, you had a question.
I'm wondering about the slope for ground transportation. Roads are crowned.
So the question about what kind of surfaces can we go over? Really very proud of our relationship with NASA. NASA Langley was actually our first customer. They are exploring the use of this technology for the manipulation of CubeSats. And it gets right to your question because they did the test. 45 degrees. 45 degrees, they were able to hold their white box on an incline. But again, we're just getting started. But another good question. One more right here? Or,
how local is the disturbance in the electromagnetic field that you're producing?
Very local. This is my iPhone. Garrett, if you please. Don't try that on a Chinese train. Okay? It's thank you. It's very, very localized. It is below center mass. In fact, it's not even measurable at this height. Coincidentally, we are in the Gauss room. Carl Friedrich Gauss, born 1777, is one of my heroes. Thanks, Carl. But Gauss is the measurement of electromagnetic energy. 10,000 Gauss is 1 Tesla. I always start spouting this kind of stuff when I get the opportunity. Anything else? Any other questions? One last question.
I have a question. So if you're going to pave the roads with copper, how much would that cost? I mean, you know, that's not like pocket money you have. That's billions of dollars to pave, you know, a couple blocks. So I was just wondering how are you going to build up the funds to do that?
It's not our objective to use copper, first of all. What we need here is about $66 a square foot, all right? For most of our applications, they're localized, right? They're in a confined area. And so we're not going to go out there and do all that. However, we cracked the code on sequestering and more efficient means of manufacturing graphene and other carbon-based conductors. There's a whole lot of science out there. In fact, we just signed an agreement for research into material studies with Hood College. And there's several other universities who we're working with to start exploring these ideas. Because what if it was just paint? Anyway, great questions. Thank you very much.